This is a review of rat number 4 of lecture 1.4. Yes, I'm rhyming and I don't mean to. I'm a poet and I don't know it. Yeah, whatever. Okay, so we've got a conversion. We want to convert 54.5 pounds to grams. I don't know the direct conversion, but they gave me kilograms to pounds. So I'm going to start always with the number given. That's the greatest technique to use in conversions or most math problems. 54.5 pounds. I'll use the abbreviation LBS. And they want grams, but I only have the conversion of pounds to kilograms, so I have to go to kilograms first. So I times it by a converting factor. I get rid of LBS, so I'm going to use my units. I'm going to cancel them away, so this pounds goes in the bottom. And there's 2.2 pounds for every what? 1 kilogram. And that's the first part. That's how I go from pounds to kilograms. Now this number reflects some number in kilograms, but I want to convert my answer to grams, so I have to do the second part. Get rid of kilogram, and I want grams. And how do grams and kilograms differ? Well, I know that King Henry died drinking, right, cat milk, but kilo hectodeca, my gram would be that kind of unit we put there as the suffix, and this differs by 3 motions. If you go to table C in your reference table, they'll give you 10 to the 3 for kilo. It means 1,000 of something. Well, that gram is that something. So it's a 1 to 1,000 ratio, and you might be tempted to put that 1,000 in the kilogram since kilo means 1,000. But remember, the bigger unit gets the smaller what number, right? These are equivalents. 1,000 grams equals 1 kilogram. So you need a lot more of these little units to equal this bigger unit when you think of that way. Anyway, kilograms are canceled and I'm left with my grams. So I get my calculator and I take my 54.5 and I times by 1, divide by 2.2, and then I times that by 1,000. You want to divide by 1, you can. And I get a raw number. And I say raw number because we're going to learn how to round these numbers soon. 24772.7. And of course, the unit left standing is your grams. And that's the answer here. Now, if you have reviewed my lecture, you know that if I'm starting with 3 significant units, I'm multiplying by converting factors that I did not measure, so I don't look at their significance. I should get back out 3 significant numbers. So this would become, okay, my 3 significant figures, 2, 4, I would need to keep 3. I look at the one behind the last one, it's above 5, so this becomes 2, 4, 8, and then I need what? Placeholders to finish out my answer. And look at this, we would round this out to 3 significant units. Okay, if you start with 3 significant figures, you should get back out 3 because we're multiplying and or dividing, but we're not considering these other numbers because we didn't measure them. They're standards. Any case, if you don't understand that, that's what tonight's lecture is about. So let's continue. Number 2, we're going to measure, and this is a 0, this is a 1, this must be 0.5. Yeah, we're going by individual tenths, 0.1, 0.2, 0.3, 0.4, 0.5. So we're certain of 0.5. We have to make a guess in between 0.5 and 0.6. This line and this line is 0.5 and 0.6. I say it's a little more than halfway, so 0.56. Now, of course, in a fill-in test, you could say 0.57 I'd accept, and of course, this is a degree Celsius, and that's why B is your answer. Okay, you have to include the guess. We're certain of 0.5, and then we guess in between our last calibration. Number 3. Okay, this one's hard because it's lower than 0. So this liquid, probably alcohol, used to be mercury, went down. So I'm going to measure the temperature. It went down from, if it was 0, it'd be here, but it went down. So it's -5, -10, -11. This line is a -11. It goes in single. So it definitely is -11, right? And then there's a little more. It looks like it's halfway between -11 and -12. So the difference between them, I'd say -11.5. Notice I don't say 11.50. I'm only picking what? One guess. I'm certain of the 11. I'm not certain of the 0.5 entirely because it's my guess. 11.50 would mean that my hundredths place is my guess, and that's not the case. So E is the answer there. Number 4 was like the other day's rat. I want to know who has the lowest amount of precision. Now you may jump and say, well, it must be 4 only because there's no lines here, but be very careful. If I measure this number, okay, this one is 98.7. Let's put that here as 98.7 degrees Celsius. This one we just did is -11.5 degrees Celsius. And this one we just did also is 0.56 degrees Celsius. What is precision, party people? Precision is about the smallest guess possible so that our answers are more similar. Well, if you notice, 3 and 4 have guesses both in the tenths place, and that is why they have the same precision. Now, number 2 has a guess in the hundredths place, which means it's more precise. Its guess is in a smaller part of the overall number. This is the most precise. The question read, who has the least precise? And that would be 3 and 4. I know you said, Mr. Grodsky, it's missing lines. Well, remember that you're guessing a tenth here, okay? And here you're guessing in a tenth, believe it or not. You're guessing in between a single integer. Here you're guessing in between a single integer. It's just blown up, okay? So the best way to look at it is look at your decimal places, all right? Let's figure out the number of significance here. Number 5, ending zeros count only if a decimal point is present. These decimal points not present, so therefore these are just placeholders, and I only have 3 significant numbers. Number 6, leading zeros never count because they're always placeholders. They help us come out to a small number. So this only has 2 significant numbers, and there's no choices that have 2. Number 7 has a decimal point, which means my ending zeros were measured. They do count, right? The whole idea behind this is trying to figure out if the zeros were measured or if they're being used in, or were they counted on or gotten from a measurement device. We know that the zeros in between numbers, sandwich zeros always count. We know that non-zero numbers had to come from the measurement device. It's these leading or ending zeros that make this a little more difficult. But these ending zeros count because the decimal point is present. So I count 1, 2, 3, 4, 5, 6, 7. 7 significant numbers. This number 8, we have a small number, and we need these zeros to get out to the small number. Leading zeros are never significant. So they're not counted as numbers we get from the device. These 2 zeros are because the decimal is present. So the ending zeros do count. The sandwich zero does count. So we count 1, 2, 3, 4, 5. Number 9, that decimal point is present. So the ending zero counts. These 2 zeros sandwiched. All non-zero numbers are significant. So everything is significant. 1, 2, 3, 4, 5, 6. 6 significant numbers. Okay. Last number, or last question I should say, is how many significant figures come from the following device? Well, let's measure. If we measure, we're certain of 40, 41, 42, 43. And we have to add the guess that we think it's on, so 43.0, and this would be milliliters. Okay, well, my friends in chemistry, how many significant figures? Well, if a decimal point is present, it was measured. Didn't we just measure it? Yeah, so it'll be significant anyway. So 43.0 is 3 significant figures. Okay, hope that helped. It's good to review these rats when you get a chance. Thank you.